So, hi everyone, so good evening. Welcome back to 1252 transportation modeling. Uh, this is our agenda for today. Okay. So you have the quiz 10 minutes a while ago. Okay. So can you present your progress report uh, for those who are ready? So if not, next week you can also present. And then we will discuss mode choice. Okay, with certain law of logic model and then traffic assignment. Yeah. So these two are the sequence of the classical four-step models, transportation demand model. Yeah. And next week you have the assignment in model. Okay. This is from trip gen until traffic assignment. And then you have also one quiz, yeah, similar to today. Okay. So how is the quiz? Is it difficult? Oh, some get 100. So it's not difficult at all, right? Okay. So yeah, the purpose of the quiz is to give a review, yeah, rather than to give judgment over your understanding. Okay. So there are comment at the bottom, so you can check what is the correct result. Okay. Okay, so we are in the topic of classical transport demand model. So, okay, so this is in the transport demand analysis. I, I hope you can see my screen. So we start with trip generation. Do you still remember what is this? So you have the socio-economic factor, okay, land use, okay, population, and then you want to know the trip attraction and trip production. That's exactly that quiz a while ago, right? And then the second step is to do what is called trip distribution. So the output of trip gen, okay, you make it a trip production and trip attraction. You put that into the uh, sum of row and sum of columns. So we have this example, right? So this is the sum of row and sum of columns, right? And then the trip distribution is to get this cell in the middle, yeah, the entries of these cells. Okay. So given the sum of rows and sum of columns, this is the trip attraction and trip production. Then you want to get the interaction and how many trips and person trips from certain origin zone to certain destination zone. Okay. Now today we'll discuss this mode choice, the third part, and hopefully if we have time, we continue with the traffic assignment. Yeah. Of course, to give you the traffic assignment, I give you the foundation. It is the shortest part. Okay, so that's the whole plan. Okay, so let's start with the mode choice. Okay, you can download the slide. So, okay, these are the content. So discuss what is mode choice, okay, what's the purpose, the factors, okay, and we go deeper into the modeling, okay, and then I'll give you some numerical examples at the end. Okay. So, say you have a city that want to implement a public transit system, okay, to reduce the car trip. Okay. Now, suppose that city generate 1 million car trip per day. Okay. Now, the survey show that 20% of the residents would consider to use public transport, and if it is available. So, question, simple as estimate. Uh, what is the reduction in car trip if the public transit is implemented? So, in that case, you have the 30%, okay, and then you have 1 million. That means potentially you will reduce around, yeah, 300,000 trips, yeah, per day. Okay, so the what is the meaning of this? Yeah? Later, when you calculate the mode choice model, what you get is this 30%. Okay, that means you still need to compute, okay, multiply by the actual person trips. Okay, so mode choice model will give you only the percentage of how many percent with zero. Okay, from one mode to another. Okay, and then you multiply that percentage with the actual person trips. Okay, so why we consider mode, right? Because a different mode will have different characteristic, isn't it? So suppose this is the simplified city, yeah. So if you are in here in the center, okay, you can only walk up to certain radius, isn't it? Right? So, and then if you use a streetcar, you can go to certain place. This is streetcar is the tram. I don't think you have it in Manila. Okay, but say you can also use cycling. Yeah, so up to certain radius. Okay? And beyond that, you need to use car. Yeah. Okay. And if you have freeway, you can go beyond certain direction. Yeah. So this is a scale, yeah, around 10 kilometer in this scale. Now, in 1 hour, you can use different mode, yeah, to reach certain kilometer. Okay. So what's the purpose of mode choice? Yeah? Remember, our input is from trip distribution, okay, with this number of trip, number of person trip, yeah, TIJ. Yeah. So from zone I to zone J, yeah, from origin to destination. Okay. So this is the input. And then you have several factors. Yeah. Later we'll discuss what are those factors. Okay. These are the input. The purpose is to determine the number of person trip, okay, not made by each mode of travel. So basically, what we are doing in mode choice is you want to compute the market share for each mode. Okay, so the input is Tij, that means the number of trips in zone I to zone J, and then the output is the same, Tij, but now divided into modes. So Tij M is the mode. Is this clear? Okay, so now what are the factors? Yeah, that we can input, or usually we input it into the mode choice model. Yeah, we can divide into three parts. Yeah, trip maker characteristic, yeah, and or the trip itself, and the transport facility. Yeah, so so the trip maker characteristic include the ownership, yeah, of vehicles, yeah, either car ownership, motorcycle ownership. Okay, so if you talk about car ownership, that means whether they are captive to certain mode. Okay, so if they don't have car, of course they are captive to public transport, yeah, or if it is available, right? So if they are having no car, so how can they use other mode? If you cannot use car if you don't have car, right? Supposed to be like that, yeah. So and depending on the income, okay. So why? Because certain income level they demand certain privacy, certain comfortability, okay? And the same thing. Study have shown that education level is actually related to the income and demanding higher. Yeah? And household structure. Yeah? When you're single, probably you're okay to use motorcycle or you use a bus. But when you have a larger family, you probably want to provide more to use car, for example. Okay, so different type of household structure will have uh, different way of thinking. Okay, and the necessity. Some people need to use car at work. So and also depending on residential density. Yeah? If the residential area is very sparse, okay, like in the US, okay, just to walk from one place to another is very far, okay, then probably they need car. So I think in Metro Manila, you can just ride jeepney within 3 minutes, maybe maximum 5 minutes. You will get yeah on the daytime, yeah. So you can get the public transport easily, yeah. But if you are in the certain residential area, then you probably have no access to public transport, then you probably don't want to use public transport. And so the type dwelling is again related to the family income and education level, and the possession of driving license. Of course, you cannot use car if you don't have driving license. Yeah. Okay. So next is the characteristic, yeah, of the trick itself. Okay. What is the purpose of the trick? Yeah? Is it optional or actually a necessity? Okay. So for optional, they have freer time, then they may use public transport, but certain necessity because of the urgency, they may need to use uh, car or motorcycle, private vehicles, and also depends on the time, okay, the day. The transport facilities characteristic, okay, that's mostly about travel time and travel cost. And this can be put into many factors. Yeah, so can be quantitative or a qualitative factor. Remember when we discussed general cost in trip distribution? So this is exactly similar. Okay. So you can put all of these quantitative and qualitative factors into generalized cost. Okay. So in quantitative factor, usually we have travel time, travel cost, and terminal cost. Okay. So travel time will include in-vehicles travel time, okay, when you are inside the vehicles, okay, and then walking time to the stops, waiting time at the stop, okay? And then transfer or interchange, okay, how many times you will transfer. And the travel costs include the fare, the fuel, okay, and then the terminal costs include the parking fee, right? Now, you can also include uh, ordinal or nominal factors, yeah, which is qualitative. Yeah. So you can include comfortability, convenience. Okay, so rating 1 to 5 or rating 1 to 10, and so on. So reliability, whether it's punctual or not. Okay, regularity of the public transport. Okay, safety and security. So when you have nominal or ordinal factors, you probably want to put it into dummy variables. Yeah. Remember last time we talked about dynamic variables, and if you have binary, so you can 0 and 1. If you have more than uh, several two, then you put dummy, okay, to compute these qualitative factors. Okay, and okay, so before this, is there any question about this? I will demonstrate to you, okay, how the model look like. Okay, let's go to the lab from here. Then you go to mode choice based on multinomial logic model. Okay, okay. So you get this, you click the links and you will get this lab. Okay. So I have many sample data here. So this is useful not only for transportation, mode choice, but any, this is data science. So basically you can have any data that you can put here, okay? And you can calculate and predict, okay, using what is called multinomial logic model. Okay, so you can start with the tutorial. So it will say that you need to select the sample data, this drop down, okay, and then you just calibrate. Yeah, when you calibrate, you will have say this is my example data. I just made it up. Okay, so this is the actual model. Okay. Now the mode is the class that you have at the end. Say I have car, bus, and bicycle. Okay. And then of course, because of this, so it will give you the probability. Probability for the car, probability for the bus, and probability for bicycle. Okay. And that depends on the factor that you input. Yeah, these are the factors that you input. Okay. So you input into this kind of table, and then it will compute for you. Yeah? When you calibrate, it will compute for you. Okay, and it will give you the model with this probability, and this model is basically 1 divided by 1 over sum of exponent of utility. So these are the utilities. Okay, and then for each of these utility, you will have the actual coefficient here, and then the t-test, the t-value. Okay, so this is just copy of that, so in the matrix form. And then you will, similar to regression, okay, you will have the overall model, okay, which is based on log likelihood ratio or similar to R squared. Yeah, this is, we call it pseudo R squared. So the explanation of this is here. So interpretation is here. Okay. Now, how to use this model? Once you have this calibrated model, so you can input new one. Yeah. So you have new one, and then you will predict. So you just click this predict to get the predicted class. Okay. And this probability table is come from the actual data that you input there. Okay. Next, okay, you have a confusion matrix, okay, whether the comparing between the true and the predicted value. Okay, and all of these are the other metrics that you can check on your own. So the interpretation is of this matrix is here, okay, and the charts also there. So I hope this is useful enough for you. So let's start with the real example data. Say you have transport mode like this. Okay, so these are the travel times in minutes. This is the cost and convenient. Okay, and we have several other mode. Yeah, so you have car, bus, and bike, right? And then you click calibrate. So you will have the result here. and then you can predict, okay, and you get the result. Is this clear or not? Okay. Next, I have another example, transport mode 2. These have different variables, right? So you have gender, car ownership level, cost, income level. Okay. So at the end, these are the classes that you put. Yeah. So you need to have the data. Okay. Based on your survey, you get this data, and then all you need to do is just input in here, and then click calibrate. Okay. Any question? Okay, you try first, and then if you have any question, you tell me. So I give you the tool. Okay, so you don't need to worry about how to compute. Okay. Yeah, it took me 1 week to build this lab. And of course, this can be useful not only for transportation. Yeah. So for example, I want to know mammal. Okay, this is the data for mammal, and then you calibrate. So of course, the probability whether this is mammal or not, yeah, depending on the different variable that you input. And then if you have new data, okay, yeah, this is in the order, yeah. So this is keeper, lay egg, can fly, live in water, and so on. Then you can predict, oh, this is uh, how many percent this is mammal, how many percent this is reptile, and so on. Of course, you will get the maximum, right? That's the classification. Is this clear? Okay, what did you learn? Yeah. So, uh, having a model, okay, this is calibrated model, right? So, calibrated means you will get uh, the values of these numbers, the coefficient, right? So, but you also need to validate. So, to validate that means you want to know, okay, if this model is actually overfit or underfit or actually fit. Yeah. So in this case, you can check. Yeah. So you can select different K fold there. Then you will get the accuracy in here. Yeah. So using predicted only, using predicted data only, you will get probably high record. Okay. But when you have foundation, that means, so in here, I have how many? What, 10-fold validation. That means the whole data set, okay, I divide it into 10, and then uh, 9 I will use for calibration, 1 for testing, okay, and then take turn, okay, each other so that each of these will have uh, chance to be tested and calibrated, each data. And then, of course, the result is actually lower than the calibration. Okay. So, but you will see that this is to tell whether this is good accuracy or not. Okay. And one more thing, uh, the actual model, the actual values here depends on very much on the computational algorithm that you use. And there are different methods to compute the optimization here. Yeah, you can use gradient descent, you can use optimization or conjugate gradient, and the result will not be the same. Okay, so once you change this different optimization, and then you calibrate again, yeah, the result will not get the same result, especially this value. Okay. So, but you stick to one method. Okay. So you only need to stick to one method. So using that method that you have calibrated, you can save the model. The next time you can use again, you just load the model. Yeah. When you save this model, you will get the JSON value or numbers of this here, this matrix. Now, for those of you who want to know the detail, okay, how did I compute this? Yeah? What is the mathematics behind this? So I give you the uh, tutorial, okay, about logistic regression. Yeah. In this case, I'm using Excel and Solver. Okay, so this is actually widely used, yeah, in many different fields, yeah, from economy, transportation, doctor science, and so on, including medicine. Okay, you can see. So, and then I explain more detail slowly because this is tutorial. So I explain what is R, right? So, and then explaining what is utility. Okay, so you can read this by yourself. Is that okay? So, and then from there, I go slowly into what is logistic function. Yeah, logistic function is this kind of verb. Okay. So like that. And then from that logistic function, we go into the probability. Yeah, this is the one that we used a while ago. Yeah. So this is basically a probability of the output y given the input x. Yeah. Okay. So these are the input x. Okay. So this is not the regression, yeah? Not just normal regression. In regression, what you have is uh, something like this, right? But your output is also numbers, isn't it? In the multilinear regression. But in logistic regression, the output is not numbers. The output is probability. So like market share. Okay. And then the probability of nominal values. Okay. So in regression, multilinear regression last time, the output is numbers. Okay. For example, the price, isn't it? But in here, the output is probability of nominal value. For example, probability of using bus, probability of using car. Can you see the difference or not? Hmm? Okay. So, and what you calibrate is actually these Greek letters, yeah? Alpha, beta, and so on. So the parameters. Okay. So how, when to use? Okay. This is the most important part. Yeah. But you use this. Okay. Your independent variable is any data type that you want. Yeah. You can have category, you can have ordinal, random, interval, and so on. But the most important is the dependent variables, the output, yeah, the y value are categorical. Yeah. Either binary or any category. Okay. This is when you will use logistic regression. Is this clear? Okay. So if you are your dependent variable is not categorical, so you don't use this. Okay. So yeah, there are other method to use also. Yeah. Now in this because this is tutorial, so I just give you two groups. Yeah. But in reality, you can calculate more than two groups. Okay, so course you calculate the parameter, yeah. So, and then you have only two groups, and then you assign to group one, yeah, if the ratio is larger than group, yeah, this ratio is actually higher. So we want to get the highest probability, basically. Okay, so this is the example. So say you want to use either car or bus, yeah. So you have a binary logistic values. And then, so finally you get this kind of model, for example. Yeah. So now if you know this value, okay. Now if you found out that the travel cost for the bus is 1.2, travel time is 30 minutes, okay, then you will ask whether this person will use bus or he will use car. That's how you predict, right? Okay. So then you input this value, okay. Then you get the probability. Yeah. So if the probability is higher than 0.5, okay, in this case, we use bus. Yeah, because this is the probability for bus. Okay. Now, if you change the fare, okay, to from 1.2 to 1.5, okay, okay, then you to check that the probability change into 0.49. So in this case, Mr. Brown will use car. It is clear or not? Hmm? So to get the parameter, okay, you can use solver. So the same data set that you have, okay, so you put it like this, and then you separate by the groups, okay, and then this is the derivation how you will get the formula, okay. So you just ignore if you don't like the math, yeah. But if you want to know the mathematics, this is the derivation, okay. So and then I put it in the Excel like this, okay. So you will get all this derivation there, okay. So you calculate that, and then you use solver to maximize the likelihood. So you need to compute the likelihood, and then you maximize that. Okay. So this is all the rest is just derivation of that values. Okay. Eventually, the one that I use is uh, the simple math here in the matrix form. Okay. So yeah, this is just to give you the brief introduction, okay, how you will model. Okay. Anyway, you have the calculator there, the online, you can just use. Yeah. Any question? Okay, let's come back to the slide. Okay. So with this introduction to the model, so you can start to, I hope, yeah, you understand that you can input all these factors, right? As long as you have the data, okay, and yeah, you put that into table, okay, you run the model, okay, and you get the coefficient, isn't it? Okay, okay. Next, in the past, okay, uh, remember we have trip gen, and trip generation is zonal, isn't it? Trip distribution is also based on zone. Yeah, zone mean maybe some district or some part of the city. Okay, so but later on we realized, okay, zonal information, yeah, which is called aggregate, is actually having some problem. Okay, then around 1980s, when people start to realize we probably don't use zonal information for more choice. Yeah, we need to make it disaggregate. Yeah, which is not based on zone but based on individual or household. Why? Why is this is what is called ecological correlation fallacy. Yeah? So this is the example. Yeah. Uh, say I have this dot in the red, okay, are the data in, zone A, yeah, for the household. And then the dot in the green is the household in zone B. Okay. If you look at the gradient, okay, what is this? This is income and this is vehicle trip per household, isn't it? So if you look at the gradient, higher income, the vehicle trip per household is actually increased, right? That's common sense, right? Okay. But because you aggregate, right? You base it on the zone. That means you take the average, right? So this is the mean. So you get only 1 point here. And then this is another point for zone B. Okay. And then from the aggregate, you get regression. What is the gradient? Down, isn't it? So you will say, oh, higher income actually less trip per household. So this is the problem, yeah, in the aggregation because you average first, okay, and then you get the regression, then you will have a problem, yeah. So using zonal, you will have trip actually decrease with income. In reality, the trip supposed to increase by the income, okay, and this aggregate is also supported, yeah, by economic, yeah, uh, what is called consumer behavior theory, yeah, which is also based on logic model. Okay, so then the lesson is simple. So you, for mode choice, use household or individual information rather than zone. Okay, so historically, again, another method was proposed, which is called modal split curve. Yeah. So this is basically telling about between car and bus, for example. Yeah. So C1 and C2 are the difference between public transport and private vehicles. Okay. And then they create similar logic model, the S curve like this. So only binary. And then they put it into the curve. So all you need to do is just to calculate the cost. Yeah, this is generalized cost, and then you minus the cost, okay, the cost difference, and then you put into this curve, and then you will get the probability, something like that. So this is called diversion curve, okay, and uh, this is very old and based on entropy maximization theory. Yeah. So the computation is the same as uh, using logic multilinear logic model, okay, which is only binary. Okay. So now we have more general than this. So you don't need this anymore. So you can just use the calculator. Okay. So that calculator, say if you have binary or multinomial legit model, so uh, this is the model. Yeah. If you have two, what you will have, so you will get, say for example, this is model one. Say one is car or bus. Okay. So you get the utility for model one, and then you divide by the exponent of utility for all models. Okay, so if you have only three, for example, car, bus, and MRT, for example, so you include all, yeah, exponent u1 plus exponent u2 plus exponent u3. Okay, so of course this is probability because now you get only the ratio. Okay, so if you have more than two modes, okay, again you can separate the utility function and then you just get this kind of formula. Okay, so exponent of certain mode that you have, and then divide by all mode. Yeah, exponent of utility of all mode. Okay, the utility value is similar to multilinear regression. That's why we call this a logistic regression. Yeah. but actually this is not regression at all. Okay, so I give you another example here, which is based on the difference. Yeah. So the data, they already make it so that instead of per bus or car, so you get the different travel costs between bus and car. So this is only two mode, because the difference. So in here we have the delta, that's the different travel cost, and the delta travel time, yeah, again the different travel time here. Okay, so example using binary logistic regression, you will have this model. Okay, so the travel cost for bus is given. The travel time is also given for the car and bus, the two of them. Okay, and then you are asked how many people will use bus if you have the TIJ. This is from the trip distribution. Okay, so you have 1,000 trip maker, yeah, between the two zones, and then what will happen if this value reduce? Yeah, so you reduce the bus fare. How many people will shift from car to bus? So this is the change in market share. Yeah, this is exactly the meaning of mode choice. Yeah. In addition, if you also put congestion pricing toll, yeah, so add it to the car, okay, and then how many people will shift from car to bus, okay? So given these values, okay, so all you need to do is input this value, okay? So you get the input, uh, the values, because this is different, so you input the difference, okay? So a while ago is 2.9 here, and then 1.7, isn't it? So you input that, so the difference is 1.2, okay? The same thing with travel time, you input, and then you get the utility value. Okay, so you will say you get 38%, 38.7. So and then multiply by the trips. Okay, then you get say 387 people. Yeah, will use bus in that zone. Is this clear or not? Okay, because you get the percentage, you multiply by the number of people, so you get the actual people who will use bus. Now, after you get this model, now you can simulate, right? Your policy, isn't it? So as urban planner or travel planner, you want to simulate the policy. Okay. So what if I change the bus fare? What if I apply some congestion pricing? Okay. So if you change the bus fare from 1.7 to 1.5, okay, the utility change, isn't it? Okay, so and then the probability change. Okay, and from that you will see there is a new number of people who you pass. So in this case, improve 2.3%. Yeah. So if you only reduce the bus fare, okay, the improvement is only 2%. Okay, but if you add congestion pricing, okay, then the car cost change, right? So in this case, there is a shift, additional 53 that people will use bus. So that means the change is 13%. Is this clear or not? So yes, you can use the same method for not just for transport, for any other computational market share. Yeah. So you work in a company, you want to get the market share of your own product, so you can also use the same method. Okay, up to here, is there any question? Yes, Justin.
Sir, for the formula of U, Is it already given or defined by?
Given here,
Yeah.
this one.
Yes, sir. So will it change if we have a different mode or different
Oh,
parameters?
yes. So a while ago, I will show you again the example in that uh, this one.
Mm.
Okay. So this is the example. Okay. If you have different data, okay, when you calibrate, this is exactly what you get. Right? So in this slide, instead of individual, okay, they use difference. So that means you already pre-computed the difference in this table because this is binary, so you can compute it. Okay? But in this example, I don't use the difference. Okay? So in this case, only for bus, only for car. So can you see the difference? Okay. In this example in the slide, okay, the data is already computed as the difference, delta. So you compute the travel cost for car, you compute the travel cost for bus, okay, and then you compute the difference. That is the one that you input in this table here. That's why the result is like that. I hope this is clear. Okay. So of course, when you have different data, you will have different numbers, yeah, of the parameters. Okay.
Okay,
So
sir.
I hope this is clear, yeah. So in this example, okay, uh, if you change because you already have the utility, right? Okay, then you will ask how many percent it will change, okay, from how many people will change from a certain mode to another mode. Yeah. So the technique is they use the difference so that you will see the change. Okay. Go ahead if you have any other question. I hope this is clear enough. So for your project, okay, or for your real work project, can you use this or not? And now think about the same model. What can you use this for? Okay. Uh, the way to do is to come back to these factors. Okay. So once you know this factor, okay, so then changing the value of this factor, meaning policy, yeah, that you will change. And then it will change the probability, yeah, the shift of demand, isn't it? Say, for example, so what happens if you have changed the fare or maybe the fuel cost and decrease or increase? Okay, it will change the demand, right? What happens if you improve the comfortability of the bus, right? So what happens if you increase the parking fee? Right. So uh, you may not be able to change this value, right? Okay, because these are the trade maker, you can only group them. Yeah, later we talk about the aggregation for each group. Yeah, so you can only group them, but uh, this factor is the policy variables because you can change this. Okay? You cannot change the family structure. Yeah, these are not policy variables. Okay? So, but they are there as input. Is okay? Okay? Then you can later aggregate them, yeah, or disaggregate them, okay? For each group, what is the model like that. But in here, these are the policy variables. Can you see that? Can you distinguish between policy variable and variable that you cannot change? Because they are inherent within the characteristic of the person or trait purpose. Okay, you cannot change that. But this one you can change, isn't it? Huh? And then this kind of change will affect the demand. So what is the whole purpose? The whole purpose is uh, you want to make shift, okay, of demand from private vehicles to use public transport. Correct or not? Why? The question is why? Why do you want to shift the demand from private vehicle to public transport? Because okay, one car, okay, usually only occupied by 1.5 people. Okay, okay, the same road width that you have, okay, or the space in the road, okay. If you use bus, probably it will have like 30 people in the same space. Because we have limited space, okay, then you try to uh, optimize this usage of the space, okay, by making them to save, yeah, toward public transport. Otherwise, not enough, okay. And now, now think about this. Okay, if the goal is actually to shift the uh, demand, yeah, from private vehicles into public transport, think about that. Uh, let's divide the population into three classes, yeah? Low income, medium income, and high income. Is that okay? Okay. Not judging, yeah, just talking about the fact. Okay. So, uh, what is the need for low income class? And what is the need of middle class? And what is the need of high income class? Based on these factors. Think about it. So to trigger your thought, yeah. Say you have very high income, okay, okay, and you have car. Maybe you have 5 cars in your house. Okay. Uh, will you and you value comfort, convenience, reliability very much? Will you go to use public transport? Yes or no? What is the probability that you will shift toward public transport? Very low. Is that correct? So if you have very high income, okay, you probably don't want to shift. You are captive to car. Okay, so public transport is not your option. Okay, so okay, conclusion number one: if you are high income, you don't go to public transport. Yeah, unless probably you change the policy. The parking fee is very difficult to get. The availability of parking in your destination is very difficult to get, or parking fee is very high. Okay, and public transport is very convenient. Then you probably want to use public transport. There is also possibility of that. Okay, so small percentage. Next, now you go to a low income class. What is the need? To be transported, right? So they don't have car. Okay, will they use car? Probably not. Okay, because they don't have, right? So they are captive to public transport. So my question to you, okay, this low income and high income class, are they your target market for your shifting from mode, yeah, private vehicle to public transport? Yes or no? Probably not, right? Why? Because they are already captive to their own choice, correct? So if you are low income, you don't change, you don't shift to private vehicle. If you are high income, you don't shift to public transport. So the point is this, okay? The the point of mode choice is actually for the middle class income. They have a car, okay? They are not captive to car, okay? They are willing to save to use public transport. Is it clear or not? Right? So your target market is not high income, your target market is not low income. Can you start to see? So now, when MRT was introduced to Metro Manila, okay, uh, it target middle class. The cost is very high to operate this, and then the price of MRT was very high, right? So people tell, why we have MRT and then we cannot use it for the low income? Okay. The problem is we want to solve traffic congestion. That's why government is creating the MRT to save the people who use car to use public transport. Why? Because this middle income class demand comfort, convenience, reliability, and so on. Can you see that? Okay. But when one of your president, maybe Estrada or something, yeah, did not have concept of mode choice, what they do, they lower the price of MRT. What happened? There is no longer comfort, convenient, the waiting very long because you reduce the cost of MRT. So the demand shifted from, okay, from middle class to the MRT, no more. So you defeat the very purpose of mode choice. Can you see that? And once you lower the cost, okay, and to return back to the actual cost is nearly political suicide. Correct. Can you see that problem? Okay. So learning this concept is important. Okay. What is your real target market in uh, mode choice? Is not the high class, not the lower class. Okay. It is the middle class. And what is the whole purpose? To solve traffic congestion. That's why you create certain mode which is for middle class, with the MRT. Okay? Can you see that whole purpose beyond the computation? I hope you understand this. Okay? Without understanding this concept, yeah, you will create the wrong policy, isn't it? Okay. And once you make a wrong policy, to come back is very difficult because there are very big public opposition. Now, the bus running parallel with the MRT in along the EDSA. What is that for? Okay. So everyone suffer because of wrong policy. Can you see that? Okay. So what is the best choice? Okay. For the low income, you subsidize. Okay. So make it free, zero cost. They can use the bus without air condition, free. If they want a better convenience, they need to pay with air condition. Okay. Okay. And then for middle class, so that they will shift from from car to public transport, you create MRT with higher cost, but higher convenience, higher comfort. Or you have a special bus, okay, with higher reliability, comfort, convenience, and so on, isn't it? So you target certain class that you have, okay. For the uh, high-income people, no matter what policy you put, they will not shift anyway. They are already captive to their car. Then you put uh, congestion pricing to them. Okay. And then the money from congestion pricing, you subsidize the poor for the public transport. Isn't that better policy? Everyone happy because you have less congested road. Okay. For the low income people, they have free transport, isn't it? For the middle class, they have better convenient transport. They are willing to pay anyway. Okay. But your current policy is the one that is mistake, isn't it? Because you pro to the poor without concept, yeah, pro to the poor. This is not actually pro. What you did is actually wrong. Okay? Because now everyone use the public transport. And then, okay, for the poor, and then the middle class have no choice to use car, okay, and then flooding the road with more congestion. That's the exact problem that you have right now. Any comment? Beyond the computation. I hope this chain of thought can be useful for you. No comment. I may be wrong, so but this is good academic discussion, isn't it? So what is your opinion? Uh, Now, no comment at all? Okay. So what can you use that model for? Hmm. What happens if you create exclusive right of way or public transport? Right. So if you do that, then you will reduce the travel time. Okay. Then you can input the reduction of travel time to the logic model a while ago. Then you will see the change in travel demand. Yeah. The same thing. You can change the fare policy, fuel tax, yeah, parking fee adjustment. Okay. All of this. Yeah. So if you have new highway, what is the impact? Okay, so the car can use better, the same thing with the bus. Okay, what is the impact of ride sharing, for example? You can compute all of this based on the same model. Okay, as long as you have the data, you can put in and you can simulate. Yeah, what if I do this? Okay. What is the actual impact? Yeah. So say, for example, you want to integrate the public transport, yeah, bus, train, probably even jeepney in one fare. Okay, you can use one card, okay, okay, and then once you just tap, go in, right, and then you have one system that include everything. So that's improve the convenience, uh, im but you need to divide among the operator, right? The money that you pay, the customer pay for public transport. Yeah. So again, many ideas that you can info public transport, you can put it here, yeah, and then compute using the same model with this. multinomial logic model. Is this clear? Okay. Next, uh, once you have the model, okay, you need to test, yeah, whether your model is actually correct or not. Yeah. So we can use the pseudo R square or likelihood ratio. Okay. So you have several model that you have. For example, you can propose this, and then if you want to compare several model, then you use R, yeah, likelihood ratio value, yeah, with certain chi-square distribution. So in that calculator, I already computed how to compute and including the t-test. Yeah. So and usually the t-test you check with this number. This come from the normal distribution, yeah, 1.96 with 5% error. Yeah. So then you check again the sign. Yeah, for each factor, you check the sign, okay, whether they are correct or not. Okay, so and then you check also whether this is a policy variable or not. Okay, if the correct sign and the significant based on the t-test, okay, uh, and then this is variable, policy variable or not is correct, then you can put include in the model. Yeah, but if this is correct sign, the value of t-test is not significant, then uh, you can put, if this is policy variable, you just remove it. It is not policy variable. Yeah. Do you understand what I mean by policy variable? Okay. The one that you changed a while ago. This one. This is the policy variable. Okay. And the socio-economic factor is not policy variable because you cannot do anything with this. You cannot change. Right? Yeah. So next, uh, if it is a wrong sign, then you have a problem. Okay. Probably you have some mistake in your data, so you check one by one. Okay. And if it is wrong sign and the t-test said this is significant, so not the absolute value of t is actually larger than 1.96, then you have a big problem, especially if this is policy variable. Yeah. So if it is wrong sign and not policy variable, you simply reject. Okay. So modeling is still R. I give you the calculator, but you still need to check the actual values and sign and the significant level. Okay. Uh, Now, any model depends on the assumption, right? So Uh, multinomial logic model have assumption what is called IIA, independent of irrelevant alternative. Yeah? It says that where any two alternative, yeah, have non-zero probability of being chosen, the ratio of one probability over the other is unaffected by the presence or absence of any additional alternative of the choice set. So, meaning they should be independent. The choices must be independent from each other. So this is example, this is the wrong example, yeah, the counter example so that you will understand. Say a city have 50% trip maker, okay, so choose between car and bus. Okay, so in this case, car and bus is the same, yeah, CC and C bus. Now the bus is painted red bus and blue bus. Okay, and then you use probability input there and put that into the same equal value, then you will have 1/3, right? But this is against the IIA, yeah. This is violating the independent irrelevant alternative. Yeah. Why? Because red bus and blue bus is actually the same. It is bus. Okay. But if you make it, uh, the three choices are not independent. Yeah, bus and car is actually independent, but blue bus and red bus actually uh, not independent. Then you will have wrong, isn't it? Probability in this case. Okay. So be careful when you put multinomial logic model. Yeah. So you don't create a three diagrams. Okay. So car and bus, and then the bus got divided into two with this blue bus and red bus, something like this. Okay. So there must be independent. Okay. Uh, Next point is when you have socioeconomic factors, right? So now question, how are you going to aggregate this? Uh, okay, so you have different trip purpose, different socioeconomic factor, right? A while ago. And we said this is not policy variable, yes. Okay, but how are we going to approach this? Okay, so there are three approaches, yeah. Naive approach is to average each independent variable, then compute the probability of its mode. And this is not good. Okay. So another way is you compute the probability for each observation, and then you average the probability of the same mode. Again, this is better, but still not good. Yeah. So what to do? Yeah. So the best approach is actually you separate the data by each socio-economic groups by trip purpose. Okay. Once you have this, so you compute the probability for each group. Okay. Then you take the average probability of the same mode. Yeah, this is the way to do. Or you aggregate all. Is this clear? If you want to separate by socioeconomic group and the purpose, this is how you will uh, aggregate them. Yeah, separate first in the data, okay, and then you calculate one by one. Okay, so you have many model for each category. Okay, and then you compute probability, and then you aggregate them by mode. Is it clear? Dennis, you want to say something?
Nothing, sir.
Nothing. Okay. So these are the example, okay, of what is the actual value of the mode choice, yeah, in different cities. Yeah. So of course, each city have different characteristics. Yeah. So this is the walking, correct, and these are the transit, and these are private cars. You see in Hong Kong, the private car is very small, mostly using public transport, right? Why? Yeah, they make it very difficult to own a car, and similar to Singapore, mm, very high cost. And then they create very good public transport so that people will use transit. Yeah, uh, yeah. Manila is still good in public transport. This is in 1999. I don't know the reason why. Okay, and this is the trend of passenger transport in Japan. Again, this is a very old study, but you can start to see the trend. Yeah, in the beginning, mostly the auto is very low, but the over time, the number of people using car is actually increasing. And this is more split percentage market share in different cities. Yeah, you can start to see this is in America, mostly private cars. In Asia, usually still have a quite good number of transit users. Okay, and this is the percentage of public transport, and this is the percentage of uh, vehicles. Yeah? And then we aggregate by different cities, okay, and then by continent. Yeah? The American cities have very low public transport and very high private vehicles, while in Asia we have tend to use public transport more. Yeah? Actually. So we are in a good shape. Uh, yeah, this is the trend, and this is not good regression, but give some ideas. So this is the car per 1,000 people, and this is the in the y-axis we have the percentage of walk trip by transit, right? So and you have many different cities. So the regression show something going down. Yeah? And this is the ridership of subway system and annual ridership, okay, in different cities. Yeah? So comparing to the population. Oh, this is the strange part. You know, so in Moscow, the ridership is more than the population. Yeah. Again, now the ridership of uh, public transport system compared to the estimated annual journey is showing here. Yeah. Manila is somewhere here on the top. Okay. And yeah, this is the trend comparing between Japan and Europe in terms of high speed train traffic. So yeah, this is all studied in 2000. But you can start to see the trend also. Yeah. It's going up and flatten in Japan, but in Europe it's getting higher over time. Yeah. Okay, so now I want to give you the computation. Okay, you will have the computation. That computation is based on PCU value. PCU means passenger car unit. Yeah, so this is based on the NCTS study in UP. So you can, I can, uh, more or less the value is this value. Yeah? Around truck and bus is around 3, isn't it? So we said car is 1, so fun is 1.5 of car. Yeah, this is based on the space. Yeah, and then motorcycle is around 0.25 probably. Yeah? 1/4 of the car in the space in the traffic. Yeah, so cheap and SUV around 2 times of the car. Okay. So each country will have their own standard. Okay. So you can check your own standard. This is just suggestion of the file that we can use. Okay. Now let's do computation. Okay. So you can open your Excel. Okay. I'll give you numerical example and then you can practice. Okay. Suppose let's give an example. Yeah, suppose we have 2.5 kilometer length. Yeah. See, this is the length, and from A to B. Yeah, from point A to point B. So this is the origin, is the destination. Suppose you have demand from a trip distribution, 13.5, yeah, 13,500 person per hour. And this is the peak. Yeah. Let's assume the link capacity 2,000, yeah, BCU per hour per lane. And one car, okay, the occupancy is 1.5 person per BCU. Question is, how many lanes is actually needed to accommodate the demand? Okay, and then what is the congestion level using that number of lanes? You remember we discussed about Green model, right, last time, right? Okay, so I give you assignment also last time. I hope you can use that. Okay, so you can use Green model to determine the travel time because you have the length. If you have the maximum speed of 60 kilometers per hour, given all of this, can compute, yeah. So, so it looks like unconnected, but you can connect, yeah. You can start to connect, yeah. So, okay, record this first so that we can start to connect. Yeah. So you have demand, right? It is 13,500. So look at the unit. So we use people per hour. Okay. And then this is actually car occupancy is 1.5. So you divide. So you will get 9,000 PCU per hour. Yeah. Because your value is still in people per hour, but to get the actual lane, number of lanes, okay, you put into PCU per hour, yeah, passenger car unit per hour. Okay, so from there you get 9,000, is that correct? Okay, and then the capacity is 2,000, right? So 9,000 divided by 2,000, so you get 4.5. Eh? So of course the number of lane must be discrete value, so you cannot use 4.5, so you would say 5 lanes. Okay, so that 5 lane will give you 5 times 2,000, that is 10,000 PCU per hour. And this is the capacity. Okay, so then you calculate the congestion. Okay, what is the congestion? Your demand, yeah, in PCU per hour, it is 9,000. Okay, and then divided by the capacity, which is 10,000. So you get the congestion 0.9. All right. So with that, how to compute the travel time? So you just plug into the Green formula. Yeah. So this is the Green formula last time. Okay. So you have the length. Yeah. So 2.5, and this is the maximum speed, right? Mu f, and then this is the congestion. Yeah. So remember the unit must be correct. So this is in hour. Okay. So when you plug into the numbers, you get 0.0633. This is in hours. Yeah. So you multiply by 60, you get 3.7, yeah, 3.8 minutes for 2.5 kilometer. Okay. So, okay, you practice first so that you understand this. Is that okay? So now, can you input this into your Excel? Okay. Then tell me what will happen if the number of people, if all of the people of these people, 13,500, okay, instead of using car, they are using bus. Okay. So one bus is the same as 3 PCU per bus. Okay. So that's a conversion. And then one bus, say 30 people per bus. Okay, so can you practice? Okay, I give you the car, but now you need to compute car and the bus, and then you compare. Okay, okay. So I give you time to practice. Yeah. If you finish, you can share your screen. Okay. Anyone want to share screen? Hmm. This is good. Yes. John Kenneth, do you want to show?
Okay, sir.
Okay. Point five.
You see my screen now, sir.
Yes, yes.
Okay, so just list down the assumptions and the exercise per car. Here. Then for bus, I use given 30 people per bus for bus occupancy. Then converting that to 3 PCU per bus.
Okay, 30, 45, okay. And then total demand is 1350, correct? Okay. And then the congestion becomes 0.65. Why the travel time is 0. Oh, okay, that's 0. That's correct. Yeah. Okay, good.
Thank you, sir.
Yes. Okay. Now, what will happen? Okay, this is you have 100% car for the same demand, right? And then you have 100% bus. Okay. So you reduce the congestion level from 0.9 now becomes 0.6, right? For the same number of lanes. Is that right? Oh no. different number of lanes. Yeah. So this is only one lane you need. Yeah. The other one is 5 lanes, isn't it? So if everyone is using bus, you only need one lane. Okay. The travel time is almost the same. But what will happen if you use the same number of lanes, say 5 lanes? Yeah. Because once you build the road, right, say you have 5 lanes already, you don't want to reduce it, right? Okay. But if everyone is using the bus, then what will happen? So you only need one lane. So then the travel time become very fast, yeah. And what will happen also, if you use the same computation here, if the bus user is not 100%, but actually only 10%, what if they only have 20%, okay, market share of the bus? The same demand, person trip, okay, but only 20% is using bus. Okay, how many lanes do you get? What is the travel time? What if 30%? What is 40%? And so on. So you can start to uh, simulate, yeah, and then get the plot. Okay. So this is what John was uh, computing a while ago, right? So you have the same demand. Okay. Now the bus occupancy is 30 bus for people. So then you will have for only 450 bus per hour. Yeah. But one bus is 3 PCU. That means you will have only 1,350 PCU. Okay. So one lane is 2,000 PCU per hour per lane. That means you only need one lane. Right? So using this one lane, then you will have 0.6, 67.5% congestion. And with this, the travel time is almost the same, but remember the space is totally different. Okay. So now, what happens if your bus user is actually only 10%, 20%, up to 100%? Okay. So the same computation, you can use data table. Okay. In Excel, there is a data table that you can use. Then you can create this kind of plot. Yeah. So this is the percentage of bus user from 0 to 100%. So the space and the number of lanes will reduce. Yeah. So from 5 lanes a while ago, okay, up to one lane, yeah, 100% a while ago. Okay. And this other space decrease as the number of percentage bus user increase. The same thing, the travel time will fluctuate down. Yeah. Okay. And the time saving from all the car is also improved. Yeah. So I'll show you. Are you familiar with data table in Excel? Or never heard about that? Okay, not familiar with that. So I will give you an Excel lessons in that case. Can you see my screen? Yes, the Excel. Right. So the yellow part here is the one that you input. Yeah? And then this is the percentage of dust. So initially it's a 100%. Okay. If this is car only and this is bus only, I just put in different place. And then this is the one that John was computing a while ago, right? So then to get the plot, so you create this, what is called data table. Okay. So to create data table, you need to input your this one. Okay. This is based on K6, which is the percentage of bus user. Okay. And then you input this one based on here, the number of lanes. Can you see this one? And then you input the, say, I want to get the travel time. Yeah. So again, you input equal to this value, yeah, the green value. And then this one also depends on this value and the saving. Yeah. Saving is just minus this value of the green car only and bus, isn't it? So once you have this input, okay, all you need to do is to add here. Yeah, so you input 0 and then you add 0.5 and so this is the percentage of the bus that you want from 0 to 100%, right? So you input this and then you highlight this and then you go to data and then use what if analysis and then data table. Yeah. Okay. Okay, you input this is the row, right? So or the columns. So in this case, you just put the columns. Okay. Then you will have all this table. Can you see? Oops. Yeah, this is unchangeable. Once you input this, it will become the values. Okay. So I have the tutorial of data table. Okay, I put that in our model. So you go here. Okay. And the Excel sheet, the one that I just showed, is already here. Okay, so you can use. Okay, so if you go to this data table, okay, you will have going to this what if analysis. Yeah? Data table in Excel. So in this example, I have depending on the number of input. Okay, you have data table of one input, the same as what we have, or you can have two input. Yeah. So let's go to one input data. So you will have like this. So this is the example of money. Okay. Why I use money? Because usually people like money. So these are the input. Yeah, present time, interest rate, year of savings, and these are the very simple formula that we use. Yeah, to calculate the future value of your money, right? And then now you want to create data table based on this input. Okay, so what you will do is get the percentage of K. The K is the interest rate, and then F here is the value, the future value here. Yeah, the same like how I put in the in macro, right? Okay, and then you input data table like this. You say what percentage of this interest rate that you want. Yeah. Okay. This is what suppose this is the what if analysis that you want to know. Okay, the same, right? So the percentage of us a while ago. And then what you will do, you highlight. So highlight means you just use a shift and then you use an arrow, yeah, to select all of this, or use mouse to select. Is that okay? Once you have selected them, go to data table in data, what if analysis, data table. Okay, and because this is in column, so you put the input cell. What is the input cell? The value in here. Okay, so okay, uh, column this. Then you will have the whole. Okay, automatically you will get the Excel will compute for you. Okay, so after that, of course, you can charge if you want. Yeah. So if you have many input, yeah, say the same the same value here. Now you want to get for the interest rate and the number of year n. Yeah. So you put 1, 2, 3, 4, 5, yeah, and then this is f. It is the future value, right? So once you have this, you select. I don't know why the picture is broken, but anyway. So you do the same thing, data table. Okay. Now you get the row input, which is the interest rate, and then the column input is the three. Yeah, the interest rate is the column, and then the row is the before, which is the year. Okay. So for each row. So and then click OK, you will get the whole data table for 2 input. Yeah, so you can do it one by one for each of them. Yeah. So once you have that, then you get everything there. And so once you have the number of lanes, so you can calculate the data table, yeah, for all of this. Yeah, one by one, yeah, per columns. Yeah. Once you have this, then you can plot. And this is your assignment actually. Can you check the assignment in Moodle? Yeah. This one, right? So the assignment is not just one zone, but now you have many, 3 zones. Yeah? So A, B, C zone, and you have the trips. So you compute, and then you got the bus, and exactly the same. Okay, yeah, clear. So I give you the example already, so you know how to compute data table. Yeah. I'll even share the Excel sheet, okay, for that example. But now you need to do for all, yeah, not just for one OD, but all OD. Okay, up to here, any question? Okay, if no question, it's your time to present your progress for your project. Can you? So any groups want to present your progress report? Just any progress that you have. Even if you don't have data, you just tell what is the current status. I hope not just the same as last time. Go ahead, you have time. Hmm. So we are in here. Who will present first? No one? No progress at all. Okay, so if no progress, maybe next week. Okay, please present your project progress report. Is that okay? Okay. That case, I will explain the next topic. Yeah, surface path and traffic assignment. Let me close this one first. Okay, can you see my screen? So this is the last step of the four-step model. Yeah? The first step is trip generation. Yeah, you have the population, you have the land use activities, okay, and then you get the trip production and trip attraction for each zone. The second step is trip distribution, meaning you want to get the interaction between zone, meaning you get OD matrix, yeah, origin destination. And then the third step is mode choice a while ago, okay, where for each person trip now, what mode they are using and percentage of the market share for each mode. Okay. Now that output of mode choice now become the input of traffic assignment. This is the first step. What is this traffic assignment? In traffic assignment, okay, now using that mode, okay, after you can convert that all into PCU value, okay, now you put that into flow on the row. Okay, so you want to know for each link, what is the flow? Okay, for each link in your network, in your road network, what is the flow in PCU per hour? Okay, but you also know the capacity of each link. That means you know the flow and capacity, then you can get the congestion. So once you get the congestion, you can get everything else, right? You can get the speed, you can get the delay, yeah? You can get the travel time and so on. Yeah. Once you have those indicator, you can also calculate the cost, you can calculate the environmental impact, you can calculate the energy, you can calculate the pollution and so on. So all these are related to each other, isn't it? Okay, so now this is the last and probably the most important, yeah, steps, which is called traffic assignment. Okay, so traffic assignment. Okay, I'll discuss what the traffic assignment, and then traffic assignment is based on the network. Okay, and then uh, most traffic assignment technique is used what is called route choice. Okay, so this is in classical paradigm. Okay, next week we will come back to IFN. Okay, but this is still in the classical paradigm, so we use route choice. Okay, so in route choice, I give you the very basic what is called all or nothing. And this is the first technique. The second technique is called multipath. And later we will also discuss capacity restraint and dynamic traffic assignment. Yeah. Okay, let's start. So again, the big picture first. Okay, so you have the value the person trips by mode, okay, from origin to destination. Yeah, so the origin is the one that produce or generate, and then destination is the one that attract. Okay, so in the traffic assignment, we want to know which path they are using. Okay, so basically this is a process allocating the traffic volume, okay, to various route of the transport network. In this case, you need the transport network as your input, yeah, represent the transport supply. Okay, then you simulate the existing and then predict the traffic movement into the real transportation network. Okay, so again, your input is basically the output of mode choice. Yeah, so you have trip distribution from each node. Okay, the node here is zone, the centroid of the zone. Okay, and then by mode. Okay, and then you convert everything into one with this PCU value. So in this case, you already have PCU, and then you assign this into network. Okay, so in that case, you need network data. Okay, so you can download the network data using the IFN transport. Okay, so you can create the network there. And in IFN transport, there is also the two methods that I mentioned a while ago, which is all or nothing and the capacity restraint. Yeah, is already there. So if you have the OD value, you can also use the same software. Okay, not only IFN. Yeah, the same software IFN transport can also use all or nothing and capacity restraint. Okay. So once you have this real network, what you will do, you put this into graph, yeah, directed graph, something like this. Okay. So this is the one that we input in the software. Okay. And then you assign, okay, the route. Yeah. You assign the route. So how do we assign the route? We need to compute the shortest route. Right? So this is the big assumption. Yeah, people not always use the shortest route. Okay, but how are you going to assign? Okay, so the simplest is to use shortest distance first initially, right? And then on the next step, you will use the shortest route in terms of time. So instead of shortest distance, now you use shortest time. Okay, so this is the computation is iterative. Yeah, first time you unload the data, so you assign little by little until it reaches equilibrium. Okay, so now the one that you put that you have the data that you have from trip with this trip purpose. Okay, and you get actually based on the mode choice is person trips, right? And then the one that you will assign is actually vehicle trips. Okay, so from the private cars, okay, then you will have vehicle trips, right? So in this case, you multiply by the occupancy. You already practiced this a while ago, just a few minutes ago, right? So the occupancy is the average person per vehicles. Okay, so of course, if you use mass transit, so I put there the occupancy is like 30 per bus, like a while ago. Yeah, if car is like 1.5. That depends on the capacity and the frequency. Yeah, the frequency represents the schedule. Okay, and then the next question is, do I assign a peak hour, which is only 1 hour, or do I assign the whole day? Yeah, so that depends on your purpose. Okay, so majority we will assign for peak hour, but your data probably 24 hours, right? So usually the peak hour is not 1/24 of whole day. Yeah, in fact, the peak hour usually around 10 to 20% of the 24 hours. So if you have average daily traffic, right, that's daily, that means per day, right? So now, if you want to put it into peak hour, then you need to decide, yeah, between 10 to 20% of that will be the peak hour traffic. Yeah, this is just rule of thumb, so you check on your own data. Yeah. More or less about this value. Okay, so and then the peak hour trip is also different from morning and evening, isn't it? So you need to consider this consideration, and then the trip generation prediction is using production and attraction, right? So be careful, okay? Because in traffic assignment, we actually use not trip production and attraction, but we use origin destination, which is from trip distribution and mode choice. Okay, so you really need to compute the trip distribution, okay? Not just trip check. And then you convert that into mode choice. Then you put this into as the input of traffic assignment. Okay, so the input of traffic assignment is actually trip matrix by mode, yeah, come from mode choice. Okay, this represents the demand. Okay, so now depending on your trip that you use, yeah, if you use 24 hours, then it is symmetric because people go will come back, right? But if you use a peak hour, then it is unsymmetrical, yeah. So going one way, and then you will have two module, one for the morning peak, okay, and then the other one is for the evening peak. Is that okay? The assignment will not be the same. Or maybe you can also have the off peak. So in that case, you have three module. Okay. So one input is the trip matrix by mode. This represents the demand. The second input is the actual network. And this comes from Google Map or GIS software, okay, or from OSM, okay, or OpenStreetMap. Okay. And this network represented by node and links. Yeah. The node represent the intersection or the centroid of the zone, okay, while the links represent the segment of the road. Okay. Up to here, is it clear? So what is the output of traffic assignment? So the output is actually link flow. Yeah. The primary output is actually link flow. So you only assign the flow to its link. That's it. Okay. Once you have the link flow, okay, then you can calculate the congestion because you have the capacity of its link, right? Okay. Once you have the link flow and congestion, then you calculate the travel cost, yeah, the travel time. Okay. Okay. From there, you can calculate the delay, okay, the speed, and so on. Then you can have aggregated value. Yeah, after for the whole network, okay, you can calculate the vehicle time, vehicle hours, clock delay. Okay, if you want to calculate the bus revenue, you can also calculate for the whole network. Okay, and secondary output, okay, you will get the route estimation. Okay, between each OD pair, that is actually internal. Okay, and you can also analyze which OD pair use particularly. Okay, so I will show you in the table station manual in very simple way. Okay, and another secondary output that you can use is actually turning movement in each intersection. How many will go to the right, left, and go straight or U-turn? Okay, so this is also a secondary output that you can get. So more disaggregate. Okay, so the network is basically based on real world network. Okay, so if the real world something like this, then you need to represent as graph. So even if the road is different, yeah, shape, okay, in the graph you probably simplify. Okay, so from here to here, you just put one node here, and this is the intersection, so you put it as one line. Yeah, so graph network representation is actually simplified of the real road network. Okay, and in the basic graph representation, you will have the node, which is also called vertex, and then you will have the link, which is also called edge. Okay, in the real graph, you may have the loop, yeah, but in transport we don't use this. Yeah, and then now. This is the topology and network connectivity, yeah, on any network, yeah, not just transportation network. Yeah. So you start to see there are certain barrier here. Yeah. This is called geographical barrier, and this is called the minimum network. Okay, so if you have the connecting all these nodes, yeah, look at this. These are the number of nodes are the same. So and then you connect only minimum connection. Okay, so you will have point A here. Okay, but if you connect everything from node to node, so you will have what is called complete network. So you have point B, D here. Okay, so in between you will have any network, and if you can plot the average path length and the network length, you will have this kind of plot. Okay, so this is topological network connectivity. Yeah, so we use directed graph. So in this case, you have nodes. It represent intersection, okay, or your house, okay? And then you have arrow. And the arc here represent the link, and this represent the connection. Is that okay? And what we say path, that means link is just direct from one node to the next. Path is actually more than that. So if you have several links you put together, this is called path. Is that okay? So for example, from 1 to 3, yeah, this is the path. So passing to node 2 and then go to node 3. Yeah. So that's the meaning of path. So route choice is to find the path. Yeah. So say this is a mountainous area, okay, and this is the highest peak. So if you go straight from 1 to 3, you will pass very difficult unless you build a tunnel. It is expensive. Okay, then you will go surrounding the mountain, right? Yeah. So then you will have several routes to select that. Yeah. So you can use A, B, and C. A is probably shorter and straight, and B is surrounding the mountain, more longer route. Okay. Now, next you need to compute the actual cost. Usually, this is how you build the road based on the actual cost of building the road. Yeah. But when we do it in traffic assignment, okay, now you calculate the route based on shortest path. Okay, so this is the table of what we call traffic assignment method. Okay, so now I divide into 4 cells. Okay, one is called deterministic. Okay, that means only no probability, or you can use stochastic. That is based on probability. Okay, and then in the row we have capacity restraint and non-capacity restraint. Capacity restraint means you have capacity that bound to get the congestion. Okay, non-capacity restraint is simple. Okay, assume no capacity at all. Okay, you just assign. Even though this is not correct, but this is the basic. So you will understand the traffic assignment. Okay, we start from all of nothing. Okay, and multi-path, even though this is not correct because there is no capacity. Yeah? So in real traffic assignment, you will use capacity restraint. Yeah, which is mostly based on wardrobe equilibrium. Okay, so we will start with all or nothing, then we go to multi-path, and then we go to capacity restraint. Yeah. So computational capacity restraint will use cost flow relationship. Okay. And then the way you load, yeah, usually we use incremental loading. Yeah. But to simplify, to understand this, I will give you first one loading time. Okay. Let's start with the simplest. Okay. All or nothing assignment. Okay, so what is this? So you assign all trips to the shortest time route and nothing to other route. Okay, not realistic, but this is the simplest. This is the basic. Anyway, even if you use the others, you will still use this. Okay, so you have the mode and the route are here. Yeah, M is mode and R. So you will assign, yeah, to the route which have minimum cost. Yeah, minimum cost in here is shortest time, and you will not assign anything to other route. Okay, how to do that? First, you compute the shortest path, yeah, for the specific OD data, and then you put all the OD flow to that path. Okay, and then you repeat again for all OD data. And then you sum, okay, the total flow for each link. I will give you example later. Yeah. So this is very simple, not realistic, but this is the basic building block for any other type of assignment. Okay. So I'll show you in one-time loading, because this is no capacity, so there is no congestion. Okay. Let's skip this part first. Okay. Later, I will discuss more detail about how you will compute the shortest path. Okay, let's skip this part. Okay. This is just to say, given the network like this, okay, you have the first node and the second node, okay, and then you will compute the shortest path. Yeah, let's skip first. Yeah. Assume that you already know using that program, you get the shortest path. Okay, so I have, let's simplify, I have only two OD, yeah. OD1 is from node 1 to 5 with 2000 flow, okay. OD2 is from node 4 to 1 with 1000 flow, okay. This is the node network, okay. And let's assume for a while, okay, that you already have this link sequence or node sequence based on shortest path. Is that okay? So I give you both link sequence and node sequence, okay? Because the number here in the triangle here, this represents the link number. Yeah, the one in the yellow in the circle, this represents the node numbers, node ID. Yeah, and this is link ID. Is that okay? They are the same thing, but make you convenient only. Up to here, do you understand or not? The input, I'm asking. Do you understand the input? So I have OD and I have the flow, yeah, and I already computed the shortest path for each OD. Is that okay? What we will do, we will assign using all or nothing. Okay, so for OD1, which is from 1 to 5, the flow is 2000. Okay, you look at this link number that I already computed. So link 1 and link 2. Yeah, it is from 135. Yeah, 135, this one. Okay, so link 1 and link 2, what we will do, you assign this whole flow to link 1 and link 2. Is it clear? And then the second OD, it is 4 and 1, yeah, from node 4 to node 1, it is 1000. Okay, you assign to the shortest path. What is the shortest path for this OD, 4 to 1? Here, link 9, link 7, and link 3. Okay, remember, yeah, link 9, link 7, and link 3. So here, link 7, link 9, and link 3. So you put that. Is it clear? So then the link flow, what you will do is you sum in each column of the link. So there you get the link flow. And this is the traffic assignment based on all or nothing. Is this clear or not? So if not clear, you give me a question or you can ask to confirm. Because if you don't understand this, you cannot understand the next point. All or nothing. Is this clear or not? So you have the flow, okay, and then you assign to the shortest path. That's it. Yeah. For each OD, you assign to the shortest path. So you compute the shortest path first, and then you assign everything there. All to the shortest path, nothing to any other route. As simple as that. Clear? Okay, good. Let's see, okay, we will use multi-path assignment. So this is the second simplest assignment, okay. Now we use logit model, the same as mood choice a while ago. We use logit model. Okay, so this is in the stochastic part, yeah. So what is the assumption here? The longer route will get smaller probability to be selected. Yeah. Remember, the first technique is called all or nothing. This is simple, but very rude, very crude. Yeah, very crude. Yeah. So this is basically only shortest path. But is it true only shortest path? Not necessarily. Yeah, people start to argue about that, right? So in this case, you assign the trip to all possible route. Wow, you need to calculate all possible route. Okay, not just the shortest route. So you calculate all possible route from O to D. Okay, and then you compute this based on how do you compute the all possible route? Based on the cost. Yeah, so this is the cost for each route, all travel time here. Okay, and then you compute the probability for each route. Okay, and the problem with this technique is if you want to compute all possible route, this is a combinatorial problem. Okay, the computation becomes very, very big and very, very long. And that's why I did not put this in the code on in transport, yeah, because it's very long to compute. And some route may have different small costs, but you still need to compute anyway. Yeah. So and the worst case, the coding strategy affect the allocation of flow. Yeah. So it tend to allocate more traffic to the dense section of the network with short link compared to the sparse network with a longer link. Yeah. So they use one-time loading, the same as traffic all or nothing, and no capacity restraint. Yeah. So there is a parameter lambda here. This is called spread parameter. So the higher parameter lambda, the higher chance to get shorter route. So okay, so I will just show you how it works so that you get idea only. Okay. So for each OD pair, like a while ago, okay, so first you get all possible route and the cost. Okay, for each route, you will have the cost, isn't it? Okay, the distance is different. Okay, in that case, the travel time is different. Okay, and then you compute the probability for each route, yeah, based on this formula, yeah, logic model. And then you assign the flow according to that probability, and then again you sum all of the flow. Okay, I give you an example. Again, the same example like a while ago. Okay, for 4 to 1, this is this, there is no other route, so this is the only route. Okay, and for 1 to 5, okay, you have many paths. Okay, this is all possible path that you put. So then you calculate the cost. Okay, for each path you calculate the total cost. Yeah? The total cost, for example, 1, 2, this one, right? 25 plus 10, isn't it? So then 35, yeah. So you calculate the cost, and then from this cost you input into this formula, yeah. Then you can get the probability here, and this is I computed by hand manually. Okay. So once you have the probability, you multiply this probability to 2000, right? Okay. Then you get the volume. Okay. So, okay. Then you input this into the multi-part assignment table, say. So because you have 1, 2, 3, 4, 1234 volume for node 1, 2, so you put there. Yeah. For the second part, 1, 6, 10, 9, so this is 37, so you put there. Yeah, and so on. Okay, and then at the end you get the sum for each link. Okay, so this is more distributed compared to all or nothing. Yeah, if you look at the assignment table in all or nothing, remember this is same OD, a lot of zeros, right? Okay, but in here you only link A is 0. Yeah, so this is better. Okay, so up to here, is this clear or not? How you assign? Okay, so I give you example here is one-time loading. Yeah. In reality, you don't use this. Yeah, this is just to give you the idea only. Okay, so what is in reality? What we use is actually cost flow relationship. Yeah, so using capacity restraint. Yeah, so typically, remember we talk about fundamental traffic flow last time. Yeah, we talk about green shield. So you get the maximum flow with this call capacity, isn't it? From there, you can calculate the link cost, which is the travel time, yeah, depending on the traffic volume, yeah, the congestion. Okay, so this is copy of last time a grid model. Okay, so we assume linear speed density and input this into fundamental traffic flow formula. Okay, and then you will get this formula of cost flow relationship based on grid shield. Okay, so this value is the G, which is the congestion, yeah, flow divided by capacity. Okay, so we discussed this last time already. So there are many other model of cost flow relationship, not just grid shield. Yeah, this is just one of them. Okay, usually the same curve. Yeah, you will have almost the same curve. Initially like linear, and then up to certain value, it will go up non-linearly. Okay, so mostly this is the behavior in real traffic. Okay, so there are many proposed cost flow function. Yeah, these are some of the proposal, but most people will use this BPR. Yeah, so the BPR function 1964 will have T0, which is the travel time per unit distance under free flow condition. So this is free flow travel time. If there is no congestion at all, in the morning, probably no other traffic, you are traveling alone. So what is your travel time? Okay, and then this is the V per QP is actually this is the congestion. Okay, but they use practical link capacity because they use HCM, yeah, the highway capacity manual, and not based on the actual computation. But anyway, it's the same. This is basically congestion. Okay, so you have the parameter alpha and beta here. Alpha is usually 0.9, 0.15. Okay, beta here usually 4. Okay. So again, there are many other model, not just this, but you can use, yeah, see in other application use different value, yeah, depend on the level of service. Okay. So if I plot it manually, I can get this kind of value. Yeah, this is for freeway and artery. Okay. So let's use this PPR formula. Okay. So we can compute. Okay. So I use in here I put 15 and 4. You can use a different value if you don't like. Okay. And then if you have a free flow speed, 60 kilometer per hour, and the flow is 2,500 and capacity 3,000. So can you calculate the travel time? Easy, just like this. And you calculate the travel time and the delay. So what is the congestion? Yeah. The flow is 2,400. Yeah. This one is vehicle per hour per lane. Yeah. And then the capacity is the same thing. So congestion is basically unitless, the same unit. Yeah. So that means 2,400 divided by 3,000. Yeah. So that's congestion. The free flow speed is 60, and you have the length, right? So if you the length, can you calculate the T0? What is the T0? Anyone? Yeah, the T0 is the travel time at free flow speed, right? If you know the distance and you know the free flow speed, then you just divide, right? Then you will get the T0. Huh? So travel time per unit distance under free flow condition. So if you know the uh, distance and you know the free flow speed, then you just divide, then you get the travel time. Yeah. So 2.5 minutes. Yeah. For this kilometer, yeah, 2.5 kilometer, you only need 2.5 minutes. But because of congestion, okay, because of the congestion, so you will travel like 17 minutes. not if if, if there is no other car, you can use 2.5 minutes, but because of congestion, you travel like 17 minutes. Okay, and the delay is like 15 minutes. Wow. And this is the effect of congestion. Yeah. Yes. Yes, yes. Very good. Yeah. Yeah. Uh, you you understand the meaning, the effect of the congestion is so much, isn't it? Okay. It happened in real life, right? It's just short distance, but you take very long time just to go, yeah, because of this congestion. Yeah. Of course, now you can change 0.9, what will happen? Okay, then you will start to see the effect. Yeah. Of course, I dramatize the value because of the alpha. Yeah. The alpha here I put 50. Yeah. Supposed to be 0.15. Okay. So using that value, okay, I want to compare the PPR with the green seal. Yeah. So if I put PPR 0.15, I will not get the same. But when I put 0.15, I will get almost the same. Yeah. The value of PPR will go down like this. But in green seal, maximum is 1. Yeah, because the capacity is really capacity, theoretical capacity. So maximum is 1. But in PPR, they use practical capacity, which is not theoretical. So it's really based on practical only. So it means can go beyond 1, yeah, to maybe 2, 3 sometimes. So in that case, there is still value. Okay. So this is in the speed. Yeah. Again, if you use 0.15, you will not get the same. But if you use 15, you will get almost the same value. Yeah. But the travel time is totally different. And the BPR will go up very fast. Okay. And if you look at this, yeah, the value is around here. Yeah. So this is almost linear, okay, beyond, and then up to 0.6 probably, yeah, and then go up very fast, yeah. So if you can plot this based on this value, I just want to compare 0.15 and 15, yeah. So yeah, so 0.15, I will get this value, and if I use 15, I will get this plot, yeah, and this is the capacity. Yeah. So if you use 0.15, it will still very high speed at capacity. Can you see that? Yeah. This is the problem with the parameter. So be careful with your parameter value. So yeah, I suggest 15. Yeah. Okay. And the same thing, if I plot the speed and travel time, they are almost the same. Yeah. There is no difference between the two of them. Okay. And this is the travel time. Between 0.15 and 15 PPR, they are very different. Yeah. So if you use 0.15, still very low internal travel time, but when you use 15, it will behavior is similar, somewhat similar to green ship. Yeah, I think this is more realistic. Yeah. Unless you define the capacity as infinite, like this. Okay. So let's practice. Okay. What happened is that that same road and that same free flow speed. Okay. Now you have average flow of 2675. Yeah, use exactly the same parameter value. Okay. So can you compute the road capacity now? If the travel time is now 10 minutes. We reverse the process. Yeah. Now you have the flow. Travel time you can measure, right? So now you want to know the capacity. And you. Oh, yeah. So the flow here is the small q is 2675, right? Okay. And the one that you want to know is the capital Q here. Right? So T0 is given, T is given 10 minutes. Right? T0 is 2.5, right? A while ago. So can you calculate? How do you calculate that? Under the exponent. Hmm. Yeah, if you calculate in Excel, you just use what if analysis, Colsic, and that's also one way, right? So easier if you use mathematics, yeah. So okay. So if you have this, right? So you input everything there, okay, and you have the mathematics here. So this is Q that you want to know. Okay. 1/5 equal to 2675 divided by Q, right? That means if this is 1/4, if this is exponent 4, then the other one is 1/4, isn't it? Then you can get the actual Q easily. Huh? So is there any question? Clear? So the same formula you can just take different way to look. Yeah. So if you know the capacity, yes, you can calculate the travel time. But what if you have the travel time, yeah, and all the parameters you set, then you can get the uh, capacity back. Okay. Next, you want to calculate the capacity restraint, yeah, the actual traffic assignment that you use. Yeah. So let's go to the actual traffic assignment with congestion. Okay. So this is based on cost flow relationship, yeah, either grid shield or PPR or any other. Okay. And this is also based on what is called equilibrium. Yeah? Similar to IFM, which based on Markov equilibrium, we have what is called wardrobe principle equilibrium. Yeah? There are two wardrobe principles. Yeah? So in that case, for each equilibrium, you will have different values. Okay. So the technique is iterative. That means instead of one-time load, okay, you do what is called incremental loading. Okay. Internally, you still use exactly the same. Okay, you still use all or nothing or multipath, okay, but you add with cost flow relationship. So what is incremental loading? That means the whole flow, for example, 2000 a while ago, you divide into small flow. And for example, you divide by 100 or you divide by 1000. Okay. So, and then this delta flow that's very small, you load using all or nothing, right? And then you compute the travel time, okay? And then again, you calculate the uh, travel time based on the cost flow relationship. Okay? And then you go again with the small flow, you input again. Is it clear? Yeah. If you use manual, this is complicated, but you can use it. Imagine the whole flow 2000 you divide by 10 is here. Yeah. So 2000 divided by 10 is 200, isn't it? So you first you load 200 and then you compute the travel time. Based on the new travel time, you load the next 200. Okay. And then you compute again the travel time. Okay. And then you load again the next 200. So now it becomes 600 until all the flow is already loaded. Clear? That's the meaning of incremental loading using iterative. And little you input the flow and then keep computing the travel time. Okay, so there are two wardrobe principle. Okay, one is called user equilibrium. Okay, so this is based on game theory, or sometimes we call it NAS equilibrium. Okay, and the second is called system equilibrium or system Pareto optimal. Yeah, so the traffic assignment step. Okay, this is where the demand meet the supply, right? So you have the demand, which is the person trip by mode, and then the supply is the transport network. So in this case, there are two possibilities. Yeah, one is you find you assign the trips, yeah, to the route so that each user will not be able to find better route. Yeah, each user are assumed to be selfish. They want to find better route. Okay, but at NAS equilibrium or a network equilibrium or user equilibrium, this is the same name anyway. Okay, the user will not find better route. This all the route are the same travel time, yeah, for each user, yeah, for each OD. So in that case, this is called user equilibrium. Okay, this is the first kind. The second kind is called system equilibrium. Okay, so then the value, the travel cost, okay, you include until it converts. Okay, but the objective is not to make the travel time equal, but to make the minimum, yeah, the minimum total travel time in the network, or the minimum delay, yeah, or the minimum travel time. So, okay, so we have two principles. Yeah, first principle, say we call it user selfish equilibrium. Okay, so in here, this is the actual behavior of the people. You understand? This is the actual behavior of the people. So we calculate the equilibrium in order so that the driver will not switch any route. In that case, the travel time is equal. Yeah, T1 equal to T2 equal to 3 time of any other route. Yeah, for each OD. Assuming the perfect information. Yeah, and then there is no other way. So they will choose this. So yeah, under this equilibrium condition, the traffic will arrange itself in the congested network so that all routes between any OD pair have equal and minimum cost. Yeah, this is assumption. Remember, yeah, traffic assignment is based on assumption. Okay, this is the first assumption. The second assumption, which is not the same, is called SO, or this is called UE, yeah, user equilibrium. This is called SO. Okay, so under this equilibrium, traffic will arrange itself, okay, in such a way so that the average total cost is minimal. So this is not based on behavior. This is based on the planner point of view. Okay, you want this as a transport planner or urban planner. You want the second one. Okay, and but the actual behavior is based on the first one. Is it clear or not? Okay, so the difference between the difference between travel time of user equilibrium and the SO is called price of anarchy. Okay, usually longer. Use if people behave user equilibrium, okay, usually much longer than SO and system optima. Okay, for many years, okay, this has been a case, and there is no cure until my book telling this that actually there is a way to solve this. Yeah, I call this premagic equilibrium. So you can check in Springer Nature. Yeah, will be published in 2026 next year January. Yeah, that we can actually integrate this. So let's come back to the capacity restraint procedure. Okay, the technique is simple, yeah. So you have the congestion level, which depends on the ratio of the travel time. Yeah, the T0 is the actual free flow travel time. This is the actual travel time that you have, which is function of congestion level, right? This is the basic cost flow relationship. Okay. Now and then we sum all of flow for our route. Okay. We calculate using user equilibrium, yeah, UE. So in this case, you want to get all the travel time, the travel cost to be the same, like this, for each route. Okay. So how to compute? This is the example. So say you have just one OD, yeah. So from node 1 to node 2, and then this is the free flow travel time, this is the capacity, okay? Then you can use this PPR function. So in here I use 0.15. Okay. So, and then you can compute that in Excel, okay? And you compute in such a way so that the travel time will be the same. Okay. Yeah. So you use solver to compute that so that the travel time will be the same. Yeah. So you will get this value eventually. Okay. And that is the value that you input. Yeah. If you have the travel time, then you will get the flow also. Okay. So I will continue this next meeting to be more detailed. Okay. But can you try to do this example at home so that you will understand first? And then if you cannot understand, you can ask question. Okay. If you come to the class blank, do not have any preparation, so you don't have question. Okay. And eventually you don't understand at all. So what is the purpose of learning in that case, right? So I hope you can start to practice for prepare before the class, then you can have a better understanding. Is that okay? Okay. So I give you the assignment and we will have the quiz about this next week also. Okay, in the beginning of the class. And last chance for the project presentation. Okay, up to here. Any question? Okay, so if not, thank you very much for today and see you next week. Yeah.